Hello and welcome to What's New in Aerospace. We're here in the Moving Beyond Earth Gallery of the Smithsonian National Air and Space Museum here in Washington, D.C. Today, with us as our guest, we have an astrophysicist from NASA Ames, Dr. Ruslan Belikov, who will be talking to us about the direct imaging of exoplanets and where we go next in studying exoplanets. But before we get to that, one of our educators, Genevieve de Messier, is going to show us a discovery station from here in the museum that demonstrates how we've discovered most of the exoplanets that we know of today.
Yes, this activity demonstrates the transit method of detecting exoplanets. So what we have here is a model of a solar system. You'll notice there's a star in the middle and planets that go around it. It could represent our own solar system, but in this case, we're talking about planets around other stars and how we can find them. One method is using the transit method. This over here represents a telescope. It represents the Kepler Space Telescope, which, like this device here, is a light sensor. It measures the amount of light it sees over time as it looks at this star. And you'll notice that as the planets go around, this solar system happens to be lined up so that the planets are coming exactly between the star and the telescope, which enables us to use the transit method. Over here on this screen, we'll show a graph of data coming from this telescope, where we have the amount of light over time. So let's start collecting data and see how the amount of light seen over time from this telescope is changing. So here's the level of light that the sensor is seeing, and you'll notice as the planets go around the star that there are dips in the level of light that is being seen there. That's actually caused by the planets going between the star and the telescope, blocking a small amount of the light. And a sensitive enough detector can actually detect that slight drop in the amount of light. The bigger the bigger the planet, the bigger the dip. So I'm going to start this again, and I'm going to predict that we'll see a medium-sized dip right now. That's when the medium-sized planet went between the star and the telescope. Here's a big dip from the big planet. So the bigger the dip, the bigger the planet, and the time between the dips tells you how long it takes the planets to go around the star, which tells you how far they are from their stars, and thus whether they might be nearby and hot or far from their stars and cool.
All right, thank you, Genevieve. And just to tell our viewers that this transiting exoplanet discovery station is something that you can see and interact with if you come to the museum, and educators like Genevieve will help you to understand and get excited about concepts like exoplanets and what we're learning about them every day. So thank you. And thank you, Russ, for being with us here today. So this is the transiting method of discovering exoplanets. And that, it's pretty incredible that we've gone during our lifetimes from wondering whether there might be exoplanets out there to now having discovered thousands of them and knowing that that's just the beginning. So,
Right.
So what's next on the horizon?
That's a great question, and maybe we can go to the first slide. The transit method that Genevieve nicely demonstrated is one of the current indirect methods of detecting exoplanets. And I would say it's generated a big wave of exoplanet discoveries in this decade, spearheaded by the Kepler mission, which you can see here. And there are also several other missions that have done Kepler discoveries. Mm-hmm. One possible next big wave of exoplanet discoveries might come from actually taking pictures of exoplanets, and that's what might be happening in the next decade or two. For example, NASA is planning a mission called WFIRST, which, among other things, would do direct imaging of exoplanets. It would also do something called microlensing exoplanet science. And then in the 2030s, NASA is studying mission concepts that would not only directly image planets, but would also directly image potentially habitable planets and start looking for life on them. There are ground-based efforts as well. You can see some of them here that have or are planning to directly image exoplanets. So it seems like in the next few decades, you'll be seeing a lot of pictures of exoplanets. And actually, some exoplanets have already been imaged. You can see on Genevieve's plot here this is what the signal that the transit method gives you from an exoplanet. And these pictures, or videos rather, show you what taking an actual picture of a planet looks like. I should point out that these planets are very large and very far from the star, so they're the easiest ones that we've detected so far. And the community is now developing instruments and looking forward to detecting potentially habitable planets and taking pictures of potentially habitable planets. And those are harder to do because they would be much closer to the star than these planets. You can see that an Earth orbit for scale would be here, and it would be much dimmer. But here's what a Earth-like planet would look like. You can see a pale blue dot orbiting a star, compared to an actual, so this is a simulated image, and this is an actual image of our Earth taken by the Voyager spacecraft from the edge of the solar system. You can see a pale blue dot suspended in the sunbeam. So to summarize, the next, or one of the most exciting next steps that I feel in this field is to obtain an image like this of another pale blue dot similar to our Earth.
So in the demonstration that Genevieve showed us, we can see that with the transit method, you can tell the size of a planet, you can tell the distance it's orbiting from the star, you can get an idea of what planets are in the habitable zone, but what can you learn from direct imaging that we are not learning from the transit method of discovering these planets?
Yeah, absolutely. So there are two key things. One is that direct imaging allows you to, in theory, with a powerful enough instrument, to detect planets in any star system, regardless of whether the planets are crossing the star or not. And as you can see from this demonstration, if you were to tilt the system, and in space systems are have random tilt, then planets may not cross between the star and your telescope, and then you wouldn't see it. And so with direct imaging, you can detect planets even if they don't cross the star, and that allows you to detect planets around pretty much any nearby star. And the second thing is it also allows you to do something called spectroscopy, which is a way to determine the composition of a planet and whether it has oxygen and water and so on, and start looking for life. The transit method also allows you to do that, but again, if you want to find life around all the nearby stars, regardless of whether they transit or not, then direct imaging is the only technology we know of that can do that.
Wow, that's great. I want to remind our audience that after we finish our discussion up here, we will be taking questions from the audience. So, in a few minutes when we get to that point, if folks want to line up at the microphone, then Dr. Belkov will be happy to answer your questions. And also, if you're watching this on Facebook Live or on the live stream and you want to send a question via that method, we'll also be taking your online questions. So tell me a little bit about the technology that you and your colleagues at Ames are working on. It's called a Coronagraph.
That's right.
And so how are you developing that, and how is that going to work?
All right, well, let me move to the next slide. And let's see. There we go. As Matt, as you said, we're working on the Coronagraph, but let me also highlight an alternative way of doing that, which is a star shade. And so there are two methods or branches of methods to take pictures of exoplanets. One, which is conceptually very simple to understand, is you just fly a shield called a star shade in front of your telescope to block the star, and then you can see a planet. The other one is called the Coronagraph, which is where instead of flying a shield outside the telescope, you block the star inside the telescope. And there are advantages and disadvantages of both methods. I happen to work on this one, although we do some work with star shades as well. But the idea behind the coronagraph is that you have a series of optics inside your telescope, like a mask and other optics and a deformable mirror to block the star and also to block diffraction, which is ripples from light that light generates when it enters the telescope, and which is brighter than your planet, so you have to remove it in order to see the planet. So that's at a high level, at least, that's how it works. And this is a kind of an image you would get from this instrument, where you see all of this light and diffraction from the star, and all of these masks and optics allow you to remove light from the star in some region and see the faint planets that are hiding in the glare of starlight.
So with the coronagraph, I mean, it sounds like it's a very technically sophisticated operation. How are you testing that and developing it, and how are you proving that it will work?
So we have a lab at NASA Ames, and also there are labs at many universities, and in particular JPL also has a nice lab testing these technologies. And so let's see if I can move on to the next slide. There we go. So our lab is one of several, and this is what some of the people in our lab, and we actually have two labs. This is one of them. In the background, by the way, you see a Kepler test demo that's going to be at the Smithsonian, I understand.
Yeah, we're working on collecting it from your lab to clear up some space for you there.
Yes. But going back to your question, how are we testing this? So we can't really test our instruments with ground-based telescopes because the problems and challenges associated with the atmosphere are very different from the challenges in space. But what we can do in the lab is we can create a star with starlight with lasers, and then pass it through a prototype of our coronagraph, our instrument, on an optical bench, and then operate it as if we were doing it in space, and then see if we can suppress the starlight to a level that allows us to see planets. And so once we can suppress it enough to where we can see planets and repeat the test in vacuum, that's when we know that we can put it on a telescope and launch it.
Yeah. So. Now, I remember when I visited you in your lab that it's a very sensitive setup that you've got. It can even detect tidal forces between the moon and the Earth, right?
Yes. Yeah, and it's amazing. And in fact, Eduardo, who couldn't be here today, has just done an experiment which was so sensitive that he could see a signal from the moon passing by. And so the level of precision that we need to achieve with these types of instruments is incredible, and it's equally incredible that we actually can achieve this level of precision. So and the reason we need our instruments to be so kind of exquisitely accurate and precise is because the brightness difference between an Earth and a Sun-like star is about 10 billion. So you have to, for every 10 billion, photons from the star, you get one photon from an Earth-like planet. So you really need to make sure everything works very precisely to remove the starlight.
So once you have the technology developed, where do you begin? Where do you want to start looking for habitable exoplanets?
Well, my favorite star is Alpha Centauri, which is the closest star to us, actually the closest Sun-like star by a wide margin. And so that's where I would like to look. But also, all the nearby stars, I think, make excellent targets. So there's a video here that shows you a star field that you would see from the East Coast. And all the highlighted stars there are stars around which we know that there are planets. But you also may see little dots that are not highlighted, and you might see that there are many more of those than highlighted stars, which means there are many stars in our neighborhood around which statistically there should be planets, but we just haven't found them, either because they're not transiting or because the planets are too small, like most of Earth-like planets are small, much smaller than the ones we found already, and are challenging to find. So even though we found close to 4,000 planets now, as you can see here, that screen is filled with highlighted stars. There are many stars nearby around which there should be potentially habitable planets, but there aren't. And also, ultimately, I think we want to search the entire galaxy. I mean, in the far future, and you can see that the highlighted stars are clustered in our galactic neighborhood, but the galaxy is huge. And even though we found 4,000 planets, roughly speaking, there are hundreds of billions of stars in our galaxy. And we know that there should be more planets than stars, which means there are many hundreds of billions of planets expected to be in our galaxy alone, and perhaps as many as 100 billion potentially habitable worlds, many of which are yet to be found. So starting with our immediate nearest stars and then expanding further, I think is what I would like to see happen.
Wow, so potentially, many habitable worlds out there. What do you think will happen once we discover our first habitable world, or our first candidate for a habitable world?
Sure. So, and it's interesting that you say candidate for a habitable world, because the direct imaging by itself, if you take a picture, it doesn't tell you if the planet is habitable or not. But it enables you to do spectroscopy. And let's see. There we go. Spectroscopy is essentially looking at the brightness of a planet, or brightness of anything really, as you change the wavelength of light or the color. And encoded in this brightness variation versus wavelength, or spectrum, is a signature of what a planet's atmosphere is composed of. And if you look at the spectrum of a Venus, Earth, and Mars, you can see that Mars has carbon dioxide, Venus has carbon dioxide, but not water or oxygen. But Earth has obvious signatures of Earth and water. So if we were to treat Earth like an exoplanet, or all three of these as exoplanets, it would be obvious that Earth has oxygen and water, and Mars and Venus do not, or at least not nearly as abundant. And on Earth, oxygen is caused by life, and it's possible to create oxygen without life, but the methods, to do that, you have to kind of think of somewhat contrived explanations of how to do that. So detecting atmospheric oxygen and water on an exoplanet would be suggestive of life, which is incredible, because you would think you had to go to a planet to detect life, but perhaps not. Perhaps you can do it remotely, and in our lifetimes we could potentially do it and figure out if life is abundant or not. However, the way I see this proceeding, as many things tend to happen in science, is that there will never be a kind of a smoking gun, or at least not at first, evidence of life. We would find suggestive signatures: oxygen, methane, water, and even those would start probably as marginal detections, and then the signal to noise would build up. And then perhaps over a decade or decades, evidence will build up to where the scientific community will say, okay, yes, this planet does indeed have life. Or the answer might come back to most planets, or all planets, do not have life, and life is rare. So look at Mars, for example. we've spent decades debating whether Mars has life or not, and whether Mars has microbes on it or not, and that question is still not closed. And I expect the same thing to happen with exoplanets. But what an exciting adventure it is to be contemplating these questions and to be on the verge of beginning to answer them. And even though there's not going to be a clear, smoking gun anytime soon, I think just the process itself is fascinating, and it's incredible to be in the generation that's doing this and that's answering these questions.
So you'd be pretty excited if we found signs of habitability on a planet at our nearest neighbor, Alpha Centauri, right? But I think a lot of people would wonder, okay, once that decade or so of scientific debate is over and we've decided that yes, there is probably life on that planet, what would we do next? I mean, how would we get there? What would we do?
Well, so getting there, of course, is very interesting and fascinating. I think that just detecting planets by themselves, even without thinking about how to get there, would already be a huge milestone for our civilization, because it would answer fundamental questions about how common life is, whether we are alone, and so on, which humans have been asking for thousands of years. And just standing on the verge of answering these questions is pretty amazing.
Yeah.
But in terms of getting there, I think that if we know that there are potentially habitable planets, and if we know there's actual real estate around other stars, I think that would provide a much greater incentive for developing technologies to go there. And perhaps it's not going to happen in our lifetimes, or even for centuries or even 1,000 years. I think that having a long-term goal of going there and having the human race expand into the stars is something that's pretty amazing to dream about.
Oh yeah, it's very exciting. Now, I've got just one last question, and then we're going to take some questions from the audience. Just a reminder that if you do have a question, please line up at the microphone over here behind this distinguished gentleman. So my last question for you is, really on behalf of maybe younger audience members or someone watching online who's thinking about, how exciting this field is and the next 10, 20, 30 years of work. How do you get into this field? What do you suggest for a young budding scientist, or maybe tell us a little bit about how you got into this field?
Yep. Well, this is a very personal question for me, because I have two daughters, an 8-year-old and a 3-year-old. Here's my 8-year-old when she was a few years younger. I would say that the most important thing is to encourage, for parents to encourage interest in science in their kids. And I'm very grateful to my parents for encouraging me to work hard and having me do a lot of math and science when I was a kid. That kind of led me to where I am today, and I'm trying to repeat that with my daughters. Not pushing too hard. It's also very important not to push them to where they start hating it. But I think more specifically, getting a firm foundation in mathematics and in physics is possibly the most important thing to do, because that then could propel you to anything you want to do in science or in engineering.
Yeah.
So make sure that you get the foundations down.
Great. Well, we're running low on time, but I think we might have time for one quick question.
Hi, I'm David Dvorkin. I work here at the museum. And I can't think of a more profound question than the one you are treating. And I think the most, for me, most meaningful thing you said was just to know that life exists out there. And let other people worry about getting there or having them get here. But my question to you is much more mundane, and it deals with the coronagraph itself. Of course, we know that coronagraphs have been around for 40, 50, 60 years now, and mainly for the sun, being able to look at the atmosphere of the sun. But in your coronagraph, you're using an occulting device inside the optical system, is that right?
That's correct.
And I'm wondering why you decided to do it that way, but also I'm curious about the rubber mirror. And not only what a rubber mirror is, but is that going to be in the vehicle that you send into space, or is that just for testing it on the ground?
Yeah, so excellent questions. Regarding the first question, why do it inside rather than outside? Right. If you were to block the star outside the telescope, the star shade that you would have to fly would have to be tens of thousands of kilometers away from your telescope. And the reason for that is that the angle between the star and the planet is very small, as opposed to the sun, where the angle is like half a degree, but the angle between a star and a planet is measured in like hundreds of milliarcseconds. So because the angle is so much smaller, that means that you have to have your outside coronagraph or star shade very far away, and that presents challenges which are not insurmountable. There's excellent technology development going on. It also means that the alternative of putting the blocker inside the telescope is also attractive.
All right.
On your second part of the question, the rubber mirror, as you call it, so it's actually not made of rubber. It's an actual mirror. It just happens to be deformable. And the reason that we need something like that is because we cannot manufacture, or technology doesn't exist to manufacture optics, normal optics, to the degree of precision that we need. But we can make a mirror that we can, an adaptive mirror that we can deform to compensate for any errors in manufacturing or misalignment, during launch and so on, to then get us the precision that we need to remove starlight.
All right.
Thank you.
Thank you for that question, and thank you, Dr. Belikov, for joining us today on the program. And thank you to our sponsor, Boeing. So once again, thank you for joining us here at What's New in Aerospace, here in the Moving Beyond Earth Gallery at the Smithsonian National Air and Space Museum. We hope you'll tune in to another one of our programs, and also, as I said before, come and see us. Come and enjoy the museum, and also all of the stuff that we have online for you to enjoy at home. So thanks again.